This is talking about magnetic and electric effects on water. So this is from the London South Bank University. All right, so I'm just going to read this out. Due to the partial covalency of water's hydrogen bonding, electrons are not held by individual molecules, but are easily distributed amongst water clusters, giving rise to coherent regions, capable of interacting with local electric and magnetic fields and electromagnetic radiation. Water, being dipolar, can be partially aligned by an electric field, and this may be easily shown by the movement of a stream of water by an electrostatic force. Very high field strengths, greater than 2.5 times 10 to the 9 volts per meter, cause water dissociation in liquid water, and hexagonal ice with slightly higher field strength, greater than 3.6 times 10 to the 9 volts per meter, causing continued proton flow in ice. And strong electric fields have complex effects on ice formation and dissociation. And between 0.45 volts per meter and 3 times 10 to the 9 volts per meter accelerates the freezing of water into cubic ice in molecular dynamics simulations by affecting the arrangement of neighbors in the second coordination shell of a water molecule. We're going to be talking about electric field strength. So this is just a very quick example or comparison. So let's just say you got these two parallel plates, and the voltage between those plates is 120 volts. Now, for comparison, a battery is about maybe 9 volts. A battery is about 9 volts, the ones that you can buy in the supermarket. The equation for electric field strength will be volts per distance. So the number of volts divided by the distance between them. All right. So if the distance between them is 5 millimeters, then it's the same as 0.5 centimeters, but remember, you need to convert it into meters. So 0.5 centimeters is 0.005 meters. Okay, so when we use the formula, volts per distance is 120 divided by the distance, which is 0.005 meters, and you get 24,000 volts per meter. So if we have two metal plates, and you've got 120 volts between them, and the distance between those two plates is 5 millimeters, that means the electric field strength will be 24,000 volts per meter. I'm just going to try and find a ruler in here, if I can find a ruler. There is no ruler on hand that I have. There's no ruler. Oh, here we are. All right, so this is a ruler. So 5 millimeters. So 5 millimeters. So can you see it's in between the 10? Sorry, it's between the 0 and the 10. So if you have two metal plates in between the 0 millimeter and the 5 millimeter, which is between there and there, and you've got 120 volts in between those two plates, the electric field strength will be 24,000 volts per meter. Compare it with a 9-volt battery. That is quite strong, isn't it? That has a strong electric field. So what would happen if you did have a 9-volt battery? So if you had a 9 volts instead, and you're dividing it by 0.005, you would get 1,800 volts per meter. So if you had a 9-volt battery connected to those metal plates at a distance of 5 millimeters, it would be 1,800 volts per meter. The self-dissociation of water decrypted, and this is published. This was published 2017, September the 10th, and this is from chemistryreviews.org. So I'm just going to read out what it says, and this is only 3 years ago, roughly. Yes, 3 years ago. All right, so let me just talk about what is dissociation first. Now, we talked about ions. What are ions? Ions are charged particles or charged atoms because they've either lost an electron or they've gained an electron. So what is an H plus ion? So a hydrogen atom has one proton, one electron. When it loses an electron, there is just one proton. So it is, the symbol for an H ion would be H plus because it's lost one electron, overall it is positive because the electron and the proton would normally cancel it out. However, because it loses the electron, you're just left with one proton, and the one proton makes it plus. So the H plus is an ion, and what's an OH minus ion? It's similar to a hydroxide, because OH is hydroxide. It's called hydroxyl ion. So what that means is that the OH minus, it has gained one electron. So what happens when you put them together? When you put the H plus ion and the OH minus ion together, you get H2O. Right, let me just read through this first. Right, so the greatest mystery of water is its own dissociation. So dissociation just means that H2O separates into H plus and OH minus. Okay, so this is dissociation. Here you've got the water molecule H2O, and it dissociates into the H plus ion and the hydroxide or hydroxyl ion. So you've got the hydrogen ion and the hydroxide ion, and that is when it dissociates. Okay, so I'm going to talk about the hydroxide ion or hydroxyl ion. They're basically the same, the hydroxide and the hydroxyl. All right, so let me talk about this. So here you have the oxygen atom is in group 6. So here you've got 6 electrons in the outer shell, and the hydrogen has 1 electron. So what happens when you put them together? So when you put them together, one of the electrons would join with the oxygen, and then there are no electrons here. So you can think of it overall, overall you can still think of it as neutral because it hasn't gained or lost any electrons yet. However, what happens if you have an extra electron here now? So here you have an extra electron and it joins there. So the extra electron would join to the oxygen, and overall it has a negative charge. So let me just repeat that again. So oxygen is in group 6, it's got 6 electrons. Hydrogen is in group 1 because it has 1 electron. What happens when if they were to join together? Then the electron would go into the oxygen, and now we will have 7 electrons. There's no electron here. And then what happens if an electron joins? So now if an electron joins, now it has a full shell of 8 electrons, but overall it has a negative charge. So that is the symbol for a hydroxide or hydroxyl ion. Okay, so let me just carry reading this on. It's not from the top, is it? Okay, so this spontaneous decomposition of water molecules into ions makes water such a good solvent, but the way in which this decay proceeds in detail and under what conditions has still been known only in broad outlines. The binding forces within water molecules are so strong that spontaneous decay is extremely unlikely. However, even pure water has a low conductivity. For every 10 billion water molecules, there are only 36 ions. The ions also tend to reconnect directly. This dynamic makes it difficult to physically detect the ionic product of liquid water. Also, simulating the disintegration of water molecules with classical simulation is impossible. What that means is that you need to use quantum mechanics. The self-dissociation is so rare that many billions of particles would have to be simulated in a computer. This exceeds the capabilities of today's hardware. Frank Weinhold, University of Wisconsin-Madison, USA, and colleagues have performed a test principles calculation and mechanistic characteristic of the ion product of liquid water Kw based on quantum cluster equilibrium QCE theory with a variety of ab initio and density functional theory DFT methods. They reduce the complexity of the model by using the fact that, okay, so you don't need to know what's before, but what's next is quite important. Using the fact that water molecules are polar and arranged in clusters in solution. So those are the two main parts. So one is that it's polar, and number 2, it is arranged in clusters in solution. Some of these clusters offer an environment in which ions feel particularly comfortable. In their model, the scientists have calculated which types of clusters are present in liquid water. From the composition of the clusters, the team concluded the probability with which the water molecules dissociate. Their method also made it possible to understand the kinetics and reaction paths through which the water molecules in the clusters decay. The model shows, for example, which proton rearrangements occur in the different cluster structures and which energies and energy barriers are important. As a result, the temperature dependence of the decay was understood. Between the melting point and the boiling point of water, the self-dissociation increases by a factor of 1000. This increase is predicted by the computer simulation and coincides with observations in nature. Okay, so I'm going to read this out. This is in relation to why when you charge a rod, when you rub the rod with a material, it becomes charged. And if we were to bring it closer to water, what happens is that it will start to bend. All right, so let me just read through this. Now, the rod is made of glass and what is generally known as a friction rod. The rod begins electrically neutral but is stripped of electrons when rubbed with a piece of silk, leaving a net positive charge behind. It is this positive electrical charge that attracts the water. Why is water so strongly attracted to static electricity? It turns out that the answer is somewhat complicated, and the complete explanation was a bit of a minor mystery for nearly 80 years. To begin our explanation, we need to look at the molecular structure of water. The chemical formula is familiar to most people, H2O, which indicates that a single molecule of water consists of 2 hydrogen atoms and 1 oxygen atom. Can you see that you've got 1 oxygen and 2 hydrogen atoms there? And also the angle between, so the centers of the hydrogen, and if you connect that to the center of the oxygen, you get 105 degrees in between. So these atoms are held together by interaction of the electric charges of the atoms, their positive nuclei and their negative electrons. If we could take a snapshot of a molecule, we would find that the atoms rearrange themselves in a somewhat asymmetric manner. Okay, so the hydrogen atoms form a 105 degree with respect to the center of the oxygen molecule. Though the molecule is overall electrically neutral, the amount of positive charge is the same as the negative charge. The oxygen atom exerts a stronger pull on the electrons than the hydrogen atoms do. Well, because there are more protons in the oxygen, so it pulls the electrons closer to the oxygen. So therefore, the electrons spend more time in the oxygen than the hydrogen. If the electrons spend more time in the oxygen than the hydrogen will become more negative and the hydrogen become more positive. Hence, you've got this electric dipole. Electric dipole means that you've got two charges, opposite and equal, but separated by distance. That is an electric dipole. All right, let me just go back down. Let's go down here. Because a dipole has a spatial structure, it also has an orientation. The direction of a dipole is typically indicated by an arrow pointing from, now it should say positive to negative, so it's from positive to negative. A dipole produces an electric field, indicated by arrows in the following picture, which in turn creates a force on other charged particles. Alright, so it is natural to ask at this point if the water is a huge collection of electric dipoles. Why isn't water visibly electric under normal circumstances? Well, because they are randomly orientated, and because it's in thermal motion, random thermal motion, overall the net charge is 0, and there's no real currents going in there. Also, because it's randomly distributed, the pluses and minus, you won't get one side more positive and you won't get the other side more negative. Okay, so the effects of dipoles pointed in opposite directions cancel out. With a large number of dipoles in all directions, they produce no electrical effect. However, what happens when you have an electric field? So this is what happens when you have the rod. It's positively charged. The negative side of the polar molecule, of the polar molecules of water, will be attracted to the positive end of the rod. So they'll align themselves. It should be noted that the alignment won't be perfect. Random motion of the molecules will prevent them from being perfectly aligned. However, if you have a stronger, so if this was stronger, then obviously it'll be more or less perfect. It'll be forced into alignment. Because if this was very strong, then the negative side will be strongly attracted and it will align more perfectly compared to if it was less positive on the rod. Okay, so the liquid in essence has a net negative charge on the side closest to the rod. So on this side will be more negative, on this side it will be more positive. The dipoles near the rod are attracted to it and in turn attract dipoles next to them, and so on, forming a chain of dipoles such that the entire body of water gets dragged towards the rod. However, this explanation is quite simple. I mean, this is what it will look like. So, however, they ran into a problem. Water is much more electrically active than the model predicts. Now, let's just go straight to the answer. So, the answer turns out to be quite complicated, but involves an effect mostly absent from the simple model described above: interactions between water molecules. So we have mentioned that in the water molecules, the electrons tend to be drawn towards the oxygen. This means that the oxygen is more negative and the hydrogen more positive and can attract each other. And it is because of this hydrogen bond. And so can you see that this slightly more positive hydrogen is attracted towards this oxygen? This hydrogen is attracted towards the oxygen from another molecule. So it forms a cluster. So this is a cluster of four water molecules connected to a central water molecule. So how does this affect the electrical properties of water? Unlike our previous description of water molecules being randomly oriented, this tetrahedral arrangement means that nearby water molecules are oriented somewhat parallel. This in turn means that when an electric field is applied, groups of molecules can move together, providing an extra oomph to their electrical properties. So the model looks like this. So here is in clusters. So with water molecules totally aligned, locally aligned, an additional effect is possible. The hydrogen bonds can then stretch the individual water molecules in a sort of tug of war. This stretching can further separate the positive and negative charges of a water molecule, increasing its electrical strength. All right, so what was it? It was only in 2007 a collaboration between workers in Princeton and Trieste finally introduced a model that agreed well with electrical properties of water at a range of temperatures and could even account for the electrical properties of ice. The strong electrical properties of water also account for its power as a solvent, able to dissolve a wide variety of other liquids and solids. Of course, these strong electrical properties also account for the very dramatic water bending shown below in the video. Now, there are some videos that show that when you have tap water, the water will still bend. Now, some have suggested that because it's from tap water, there are ions in the water itself. So, I mean, it has been suggested that because there are ions in the tap water, it is not because of the polar molecules.